Right, what we're going to do now is look at benzene and its reactions. We'll start off by looking at the basic structure of benzene, and then we'll look at the type of reactions that benzene undergoes, and we'll look at a general reaction scheme for the mechanism. Alright, so let's start off with looking at the basic structure of benzene. You probably know already that benzene's formula is C6H6, and if you was to look at the structure, it would be a hexagon like this. Every single carbon is bonded 3 times, as you can see. Look, each carbon is bonded to once, twice, 3, and because carbon's in group 4, it has 1 electron left over, and that 1 electron becomes detached or delocalized off the carbon and can float in the ring. Every single carbon releases 1 electron into the ring, so you can imagine this ring is very highly negatively charged. Okay, right, so we can represent benzene like this hexagon with a circle inside representing the delocalized electrons. Alright, this is the modern way of looking at benzene. Kekulé first suggested benzene to be like this, as cyclohexatriene, alternate single and double bonds, like so, but a couple of pieces of evidence, for example, will disprove that. First of all, carbon-carbon bond lengths are all the same. Every single carbon bond length is the same, whereas Kekulé's benzene would mean that there would be short bonds, short bonds, long bonds, etc., because carbon-carbon bonds, double bonds, are shorter than carbon-carbon single bonds, but in fact all of them are the same length. So that disproves Kekulé's benzene structure. That's one piece of evidence. Another piece of evidence which disproves Kekulé's structure is the hydrogenation, thermochemical evidence. If you was to hydrogenate benzene, if you was to add hydrogen to this, you'd get cyclohexane. If you hydrogenate this one, cyclohexane, and you would release 360 kilojoules of energy by hydrogenating this one. When you hydrogenate benzene, you only get 208 kilojoules of energy released, which shows you that benzene is actually more stable than this structure would suggest. It's 152 kilojoules more stable, and this energy is sometimes called the stabilization energy of benzene. So there you are. There's a couple of pieces of evidence to show that benzene is actually like this and not like this. Right now, benzene like this is very, very stable, so when it does react, it will want to keep the ring structure, so it will undergo substitution reactions and not addition. Okay, so the type of reactions it undergoes are substitution. Also note, because it's very negative, a high amount of negative charge in the ring, then electrophiles will want to come and attack it. Negative loving species will come and attack the benzene ring. Positive ions, like this, will want to come and attack it. So electrophiles, negative loving species, and it'll undergo substitution reactions. Now we need to know the mechanisms of 2 or 3 reactions, but in general we can represent the electrophilic substitution in this kind of way. So first of all, there will be the equation to make the electrophile. Secondly, the electrophile will then attack the ring, and then finally a proton will be eliminated. So here's an example. Look, benzene with the electrophile, there it is, and a H plus had to come off, substitution, and the ring is maintained. Okay, let's have a look at the mechanism and how you might do that on paper. So here's electrophile, and the process is an electron pair comes out to meet the electrophile, like so, causing this intermediate to form. There's the electrophile attached to the carbon. There is also a hydrogen on that carbon which will be released. what happens then, you got this intermediate form of benzene which has a positive charge in the middle, as you can see. Notice that I've drawn the horseshoe to cover all of the carbons except for this one here. So you must draw it fairly fully all the way around in the ring except for that part there. Right. Now electrons have to be released back into the ring like this as the hydrogen is removed, and when you do that the ring is replenished and you've got your final product, and there's the H plus that was removed, substituted. Electrophiles, some examples, you've got nitronium ion, NO2+, if you want to make nitrobenzene. You've got chlorine ions, bromide ions as well, positive, they're all positive. You've got acyl ions and alkyl ions. And here are a couple of examples of them. Let's look at the formation of a couple of these ions. We need to know the equation for the formation of the electrophiles. First of all, the formation of the nitronium ion is concentrated sulfuric and concentrated nitric acid react together to make your electrophile, plus you get this HSO4 minus ion and water, and this then goes on to attack the benzene ring. If you want to make a Cl plus ion or a Br plus ion, you'll have to react this chlorine molecule or bromine molecule with your catalyst, AlCl3 each time, and you get AlCl4 minus and your electrophile. This is called a halogen carrier because it'll take care of it'll hold one Cl minus ion for you, while the other Cl ion, Cl plus ion, will go on to attack the benzene ring. Right. If you want to make an alkyl ion, again you'd use the same halogen carrier, AlCl3 catalyst, and you get the electrophile and your AlCl4 minus. Acyl ion, in the same kind of way. Now I would practice writing equations to make those electrophiles. Let's look at, just compare benzene with methyl benzene. Then we'll have a look at a mechanism. Methyl benzene. Now you may be asked to compare the reactivities of the benzene and the methyl benzene. Now if you look at the methyl group is has a positive inductive effect in that it releases electrons into the ring, pushes electrons into the ring, making the negative charge in the ring greater. If it's greater in here now, it's more susceptible to attack by the electrophile. So electrophiles are more likely to attack it, and so this is a faster reaction than this one here. Okay, so let's look at a mechanism. Let's say we want to acylate benzene. Here it is, acyl group. So I've got ethanoyl chloride, and I've got my catalyst, aluminium chloride. Make my electrophile, and I've got my AlCl4 ion here. Right, here's the electrophile. Comes along to the benzene ring. The benzene ring extends a pair of electrons out to meet the electrophile, and it forms this intermediate. Remember, the horseshoe has to cover all of these carbons. Positive sign in the middle, which has to be neutralized, and the electrons from the carbon-hydrogen bond come into the ring, and the H plus is released. Here it is. Okay, and here's your final product, and you get Cl minus and AlCl3 reformed. So hence it's a catalyst because you get it back again. Okay. Here's a question that you can try having done those notes. Write an equation to show the formation of an electrophile, which you can do now. Outline a mechanism for this reaction of this electrophile with methyl benzene to produce 4-methyl nitrobenzene. Have a go at that question. Look back at the notes. Name and outline a mechanism for the production of ethyl benzene from benzene. We know what that is. Electrophilic substitution. Outline the mechanism. Have a go. Practice it. And first write an equation to show the formation of the reactive intermediate. That's formation of the electrophile. Again, have a look back. Benzene reacts with ethanol chloride to form that one there. Aluminium chloride is the catalyst. Write an equation to show the role of aluminium chloride in this reaction. We know it's a catalyst because it's reformed at the end. Okay, outline a mechanism for this reaction of benzene. Again, you can practice that. And when methyl benzene reacts with ethanol chloride and aluminium chloride, the reaction is faster than with benzene. And the question is why, and we've gone through the reason for that. The methyl group has a positive inductive effect, pushing electrons into the ring, making it more negative and susceptible to attack by electrophiles. Okay, so there we are. We've had a look at the basic structure of benzene and the type of reactions and why those reactions happen, and we've also seen a general scheme for the mechanism.